Welcome friends. In this session, we introduce the concepts of cyclic subgroup and cyclic groups. We describe that all the elements in a cyclic groups can be generated by a single element. A discussion of structure of finite and infinite cyclic groups will be made. Cyclic subgroups. We first describe a theorem that provides a smallest subgroup associated with an element in a group. Theorem 1. Let G be a group and let A belongs to G. Then H is equal to set consisting of A raised to n such that n belongs to set is a subgroup of G and is the smallest subgroup of G that contains A. That is, every subgroup containing A contains H. If the operation in the group G is addition, the above H is equal to set consisting of NA such that n belongs to set. Proof. We check the three conditions for a subset of a group to give a subgroup. 1. Let x, y belongs to H. Then x equal to A raised to R and y is equal to A raised to S for some R S belong to set, and xy is equal to A raised to R into A raised to S is equal to A raised to R plus S with R plus S belongs to set. Hence, xy is again in H. Since x and y are arbitrary elements in H, this shows that for every x and y belongs to H, the product xy belongs to H. Thus, H is closed under the group operation of G. 2. To show that the identity element in G also belong to H, we first note that if E is the identity element in G, A belongs to G has the inverse A inverse belongs to G such that A into A inverse belongs to G. That is, A raised to 1 into A inverse belongs to G. For obvious symbolic reasons, we agree to take A raised to 0 is equal to E. Now, since E is equal to A raised to 0, with 0 belong to Z, we have E belongs to H. 3. For A raised to R belongs to H, A raised to minus R belongs to H, and A raised to minus R into A raised to R is equal to A raised to minus R plus R is equal to A raised to 0 is equal to E. Hence, for any x belongs to H, x inverse belongs to H. That is, for every element in H, its inverse also in H. Hence, H is a subgroup of G. It remains to show that H is the smallest subgroup of G that contains A. For this, it remains to show that every subgroup containing A contains H. Any subgroup of G containing A must contain A into A is equal to A square by the closure property. Similarly, it must contain A square into A is equal to A cube into A is equal to A raised to 4, etc., A raised to n for any positive integer n. We note that in additive notation, An would mean Na. Of course, any subgroup containing A must contain its inverse A inverse, and then A inverse into A inverse, which we denote by A raised to minus 2, and in general it must contain A raised to minus n for all positive integers n. Any subgroup containing A must contain the identity E is equal to A raised to 0 of G. We summarize that any subgroup of G containing A must contain all elements A raised to n for Na in the case of additive groups. For all n in Z, that is, a subgroup containing A must contain A raised to n such that n belongs to Z. That is, every subgroup containing A contains H. This completes the proof of the theorem. Definition. The subgroup H is equal to set consisting of A raised to n such that n belong to Z of theorem 1 is the cyclic subgroup of G generated by A and is denoted as follows. It is read as cyclic subgroup generated by A. Remark. Obviously, H is equal to set consisting of A raised to n such that n belong to Z has a generator A. The inverse A inverse is also a generator because A raised to minus 1 whole raised to minus n is equal to A raised to n. Cyclic group. Definition. An element A of a group G generates G and is a generator for G if cyclic subgroup generated by A is equal to G. A group G is cyclic if there is some element A in G that generates G. That is, A group G is cyclic if G is equal to cyclic subgroup generated by A for some A belongs to G. Example 1. Show that the group Z4 is cyclic while the clean 4 group V is not. Solution. Consider Z4 is equal to set consisting of 0, 1, 2, 3. Now 1 belongs to Z4 and consider H is equal to set consisting of n into 1 such that n belongs to Z. Then since 1 into 1 is equal to 1, 2 into 1 is equal to 1 addition modulo 4 1 is equal to 2, 3 into 1 is equal to 1 addition modulo 4 1 addition modulo 4 1 is equal to 2 addition modulo 4 1 is equal to 3, 4 into 1 is equal to 1 addition modulo 4 1 addition modulo 4 1 addition modulo 4 1 is equal to 3 addition modulo 4 1 which is equal to 0, etc. We have H is equal to set consisting of 0, 1, 2, 3 which is equal to Z4, showing that 1 is a generator for Z4 and hence Z4 is a cyclic group and subgroup generated by 1 is equal to Z4. The clean 4 group is V is equal to set consisting of E, A, B, C. We note that A square is equal to A into A is equal to E, A cube is equal to A into A is equal to A square into A is equal to E, A raised to 4 is equal to E and so on. Hence, subgroup generated by A is equal to set consisting of EA and so subgroup generated by A not is equal to V. Hence, A is not a generator for V. Similarly, it can be seen that subgroup generated by B is equal to set EB and subgroup generated by C is equal to EC, showing that B and C are not generators of V. Since V has no generator, V is not cyclic. We conclude that Z4 is a cyclic group of order 4 while V is a group of order 4 which is not cyclic. Example 2. Give all the generators of Z4 and all cyclic subgroups of Z4. Solution. By example 1, 1 is a generator for Z4. Now consider 2 belong to Z4. Then cyclic group generated by 2 is equal to set consisting of n into 2 such that n belong to Z. And since 1 into 2 is equal to 2, 2 into 2 is equal to 2 addition modulo 4, 2 is equal to 0, 3 into 2 is equal to 2 addition modulo 4, 2 addition modulo 4, 2 is equal to 2, 4 into 2 is equal to 2 addition modulo 4, 2, addition modulo 4, 2, addition modulo 4, 2 is equal to 0 and so on. We have subgroup generated by 2 is equal to set consisting of 0, 2 which is a proper subgroup of Z4, showing that 2 is not a generator for Z4, but set 0, 2 is a cyclic subgroup generated by 2. Consider 3 belong to Z4, then set consisting of n into 3 such that n belongs to Z4 and since 1 into 3 is equal to 3, 2 into 3 is equal to 3 addition modulo 4, 3 is equal to 2, 3 into 3 is equal to 2 addition modulo 4, 3 is equal to 1, 4 into 3 is equal to 0 and so on. We have subgroup generated by 3 is equal to set consisting of 0, 1, 2, 3 which is equal to Z4, showing that 3 is a generator for Z4. Hence, the generators for Z4 are 1 and 3. Also, the cyclic subgroups of Z4 are Z0, Z02 and Z4. Example 3. Discuss all the cyclic subgroup of the clean 4 group V. Solution. The cyclic subgroup of V are set E generated by E, set EA generated by A, set EB generated by B, set EC generated by C. The lattice diagrams given below indicates the subgroup of the group Z4 and V. Example 4. Examine that the group Z of integers under the operation addition is a cyclic group. Find all generators for Z. Solution. 1 belong to Z and cyclic group generated by 1 is equal to set consisting of n into 1 such that n belong to Z, which is equal to set consisting of etc. -2, -1, 0, 1, 2, etc. which is equal to Z, showing that 1 is a generator for Z. Hence, Z is cyclic. Since 1 is a generator, its inverse -1 is another generator. Also, it can be seen that there is no other generator for Z. Example 5. Consider the group set of integers under the operation addition. Find subgroup generated by 2, subgroup generated by 3 and subgroup generated by n. Solution. Note that 1 into 2 is equal to 2, 2 into 2 is equal to 2 plus 2 is equal to 4, 3 into 2 is equal to 2 plus 2 plus 2 is equal to 6, etc. 0 into 2 is equal to 0, minus 1 into 2 is equal to minus 2, minus 2 into 2 is equal to minus 2 plus minus 2 is equal to minus 4, etc. Hence, subgroup generated by 2 is equal to set consisting of etc. minus 6, minus 4, minus 2, 0, 2, 4, 6, etc. The set of integer multiples of 2. Similarly, it can be seen that subgroup generated by 3 is equal to set consisting of etc. minus 6, minus 3, 0, 3, 6, etc. The set of integral multiples of 3. Continuing like this, it can be seen that subgroup generated by n is equal to set consisting of etc. minus 3n, minus 2n, minus n, 0, n, 2n, 3n, etc. The set of integer multiples of n. Usually we denote the cyclic subgroup generated by n by nz. Example 6. Let n be a positive integer and let un be the multiplicative group of the nth roots of unity in z. Then un consists of the numbers given by cos 2 pi r by n plus I sin 2 pi r by n is equal to e raised to I 2 pi r by n. R is equal to 0, 1, 2, etc. n minus 1. We take alpha is equal to cos 2 pi by n plus I sin 2 pi by n, which is equal to e raised to I 2 pi by n. Hence, the integral powers of alpha can give all the nth roots of unity. Hence, alpha is a generator of un and un is a cyclic group. The elements of un can be represented geometrically by equally spaced points on a circle about the origin as illustrated in figure 2. The heavy point represents the number alpha. The geometric interpretation of multiplication of complex numbers shows at once that as alpha is raised to powers, it works its way counterclockwise around the circle, landing on each of the elements of un in turn. The group un is obviously a subgroup of C. Also, it can be regarded as a subgroup of the group U of all complex numbers set where mod z is equal to 1 under multiplication. In particular, when n is equal to 1, u1 is equal to set consisting of 1 and is a cyclic group of order 1. When n is equal to 2, u2 is equal to set consisting of 1 minus 1 and is a cyclic group of order 2. Minus 1 is its generator. Attention, 1 is not a generator for u2. When n is equal to 3, u3 is equal to set consisting of 1 omega, omega square and is a cyclic group of order 3. With generator, omega is equal to cos 2 pi by 3 plus I sin 2 pi by 3. Being the multiplicative inverse of omega, omega square is also a generator. When n is equal to 4, u4 is equal to set consisting of 1 I minus 1 minus I is a cyclic group of order 4. I is a generator, minus I is another generator. Attention, 1 and minus 1 are not generators for u4. Order of an element in a group. Definition, let A be an element of a group G. If the cyclic subgroup generated by A of G is finite, then the order of A is the order of the cyclic subgroup generated by A. If the cyclic subgroup generated by A of G is infinite, we say that A is of infinite order. Remark, the order of the generator of a finite cyclic subgroup is the order of the cyclic subgroup. Example 7. Order of the element 1 in Z4 is 4. Since 1 is the generator of the group Z4 whose order is 4. Order of the element 2 in Z4 is 2. Since subgroup generated by 2 is equal to set consisting of 0, 2. Have order 2. Example 8. Order of the element minus 1 in U4 under multiplication is 2. since subgroup generated by minus 1 is equal to set consisting of 1 minus 1 have order 2. Example 9. The element 1 in set is of infinite order since subgroup generated by 1 is equal to set is of infinite group. Alternate definition for order of an element. Let A be an element of a group G having identity element E. Then the order of A is the least positive integer n such that A raised to n is equal to E. If no such positive integer exists, then A is said to be of infinite order. Example 10. Using the alternate definition, the order of minus 1 in U4 is 2. As minus 1 raised to 2 is equal to 1, the identity element in U4. Similarly, the order of 2 in Z4 is 2, as 2 into 2 is equal to 2 addition modulo 4 2 is equal to 0. Cyclic groups and generators. We now describe some properties possessed by cyclic groups. Theorem 2. Every cyclic group is abelian. Proof. Let G be a cyclic group and let A be a generator of G so that G is equal to group generated by A is equal to set consisting of A raised to n such that n belongs to set. We have to show that for G1, G2 belongs to G, G1, G2 is equal to G2, G1. If G1, G2 belongs to G, then there exist integers R and S such that G1 is equal to A raised to R and G2 is equal to A raised to S. Then G1, G2 is equal to A raised to R into A raised to S, which is equal to A raised to R plus S, which is equal to A raised to S plus R, as R plus S is equal to S plus R by the commutativity of addition of integers, which is equal to A raised to S into A raised to R, which is equal to G2 into G1, so that G is abelian. In the proof of the following theorem, we need division algorithm for set. If m is a positive integer and n is any integer, then there exist unique integers q and r such that n is equal to mq plus r such that 0 less than or equal to r less than m. Theorem 3. A subgroup of a cyclic group is cyclic. Proof. Let G be a cyclic group and let A be a generator of G and let H be a subgroup of G. If H is equal to set consisting of E, then E is a generator for H and hence H is cyclic. If H naught is equal to set E, then there exists some element other than E, say A raised to n belongs to H for some positive integer n. Let m be the smallest positive integer such that A raised to m belongs to H. Claim C is equal to A raised to m generates H. We must show that every B belongs to H is a power of C. Since B belongs to H and H is a subgroup of G, we have B is equal to A raised to n for some n. We have to show that B is a power of C is equal to A raised to m. For this, we show that there is some integer k such that n is equal to mk, and then A raised to n is equal to A raised to mk is equal to A raised to m whole raised to k. By division algorithm for the set of integers, there exist integers q and r such that n is equal to mq plus r, 0 less than or equal to r less than m. Then A raised to n is equal to A raised to mq plus r is equal to A raised to m whole raised to q into A raised to r. So, A raised to r is equal to A raised to m whole raised to minus q into A raised to n. Now, since A raised to n belongs to H, A raised to m belongs to H and H is a group, both A raised to m whole raised to minus q and A raised to n are in H. Thus, by the closure property, A raised to m whole raised to minus q into A raised to n belongs to H. Hence, A raised to r belongs to H. Since m was the smallest positive integer such that A raised to m belongs to H and 0 less than or equal to r less than m, the fact that A raised to r belongs to H forces us to conclude that r is equal to 0. Thus, n is equal to q into m and b is equal to A raised to n is equal to A raised to m whole raised to q, which is equal to c raised to q. So, b is a power of c. Since b is an arbitrary element in H, This shows that any element in H can be expressed as a power of C. Hence, C generates H and hence H is cyclic. This completes the proof of the theorem. Corollary. The subgroups of set under addition are precisely the groups n set under addition for n belongs to set. Proof. By example 4, set under addition is cyclic with 1 as a generator, and for each n belongs to set, n set is equal to set consisting of etc. minus 3n, minus 2n, minus n, 0, n, 2n, 3n, etc. is a cyclic subgroup of set, and n set is equal to cyclic subgroup generated by n. Also, by theorem 3, every subgroup of a cyclic group set is cyclic. Let H be any one subgroup of set, then H is equal to subgroup generated by n, which is equal to n set for some n belongs to set. Thus, the subgroup of set under addition are precisely the groups n set under addition for n belong to set. The structure of cyclic groups. Let G be a cyclic group with a generator A. Two cases arise. Case 1. G has infinite number of elements. In this case, we claim that no two distinct exponents h and k can give equal elements a raised to h and a raised to k of G. Suppose a raised to h is equal to a raised to k and say h greater than k, if then just interchange h and k. Then a raised to h minus k is equal to a raised to h into a raised to minus k, which is equal to e, the identity, and h minus k greater than 0. Let m be the smallest positive integer such that a raised to m is equal to e. We claim that G would then only have the distinct elements e, a square, etc. a raised to m minus 1. Let a raised to n belongs to G. By division algorithm, there exist integers q and r such that n is equal to mq plus r, 0 less than or equal to r less than m. Then a raised to n is equal to a raised to mq plus r, which is equal to a raised to m whole raised to q into a raised to r, which is equal to e raised to q into a raised to r, which is equal to a raised to r for 0 less than or equal to r less than m. This would mean that G has only m number of elements e, a square, etc. a raised to m minus 1, so that G would be finite, contradicting our assumption that G has infinite number of elements. Thus, when the cyclic group G has an infinite number of elements and A is a generator of G, then all powers of A are distinct. Case 2. G has finite number of elements. Then the order of A is finite. In this case, we claim that not all positive integral powers of A, generator A of G, can be distinct. So, for some exponent h and k, we must have a raised to h is equal to a raised to k. Proof of the claim. Suppose that all positive integral powers of a generator A of G are distinct. Then a raised to h not is equal to a raised to k for all h k belongs to set, so that a raised to h minus k not equal to e. Hence, a raised to n not is equal to e for all n belongs to set, showing that the cyclic group generated by A is equal to G is of infinite order, contrary to our assumption. Theorem 4. The set Zn is equal to set consisting of 0, 1, 2, etc. n minus 1 is a cyclic group under addition modulo n. Proof. Let A, B, C belong to Zn. By the definition of addition modulo n, A addition modulo n B is equal to R, where R is the non-negative remainder obtained when the usual sum A plus B is divided by n, so that 0 less than or equal to R less than n minus 1. Hence, Zn is closed with respect to the operation of addition modulo n. G1. Associativity. A addition modulo n B addition modulo n C is equal to the non-negative remainder obtained when A plus B plus C is divided by n. which is equal to the non-negative remainder obtained when a plus b plus c is divided by n, which is equal to a addition modulo n, b addition modulo n c. Existence of identity element. 0 belongs to set n, and for every a belongs to set n, we have 0 addition modulo n a is equal to a addition modulo n 0. Existence of inverse. Clearly, the inverse of 0 is 0. For a given non-zero a belongs to set n minus a belongs to set n, and a addition modulo n minus a is equal to 0, which is equal to n minus a addition modulo n a, showing that the inverse of a belongs to set n is n minus a belongs to set n. Hence, set n is a group under addition modulo n. As the commutativity also holds, set n is an abelian group under addition modulo n. Also note that 1 belongs to set n, and 1 addition modulo n 1 is equal to 2, 1 addition modulo n 1 addition modulo n 1 is equal to 3, etc. 1 addition modulo n, etc. addition modulo n 1 n minus 1 times is equal to n minus 1. 1 addition modulo n, etc. addition modulo n 1 n times is equal to 0. Therefore, 1 is a generator of set n, and hence set n is a cyclic group of order n. Subgroups of finite cyclic groups. Theorem 5. Let G be a cyclic group with n elements and generated by A. Let B belongs to G and let B is equal to A raised to S. That is, if order of G is equal to n, G is equal to subgroup generated by A, B is equal to A raised to S, and H is equal to subgroup generated by B. Then order of H is equal to n by D, where D is equal to GCD of ns. Proof. By theorem 1, B generates a cyclic subgroup H of G. It remains to show that H has n by D elements. Following the argument of case 1 in the section the structure of the cyclic group, we see that H has as many elements as the smallest positive power m of B, that gives B raised to m is equal to E. Hence, our job is reduced to find the value of m. By assumption, B is equal to A raised to S. Hence, B raised to m is equal to E if and only if A raised to S whole raised to m is equal to E. That is, if and only if n divides ms. Now, our aim is to find the smallest positive integer m such that n divides ms. Let D be the GCD of n and s. Then there exist integers u and v such that D is equal to un plus vs. Since D divides both n and s, we may write 1 is equal to u into n by D plus v into s by D. Equation number 1, where both n by D and s by D are integers. The last equation shows that n by D and s by D are relatively prime. For any integer dividing both of them must also divide 1. We wish to find the smallest positive m such that ms by n is equal to m into s by D by n by D is an integer. From equation 1, there is no common factor for s by D and n by D. Hence, to make ms by n an integer, n by D must divide m. So, the smallest such m is n by D. Thus, the order of H is n by D. Remark. When the operation is addition, B is equal to A raised to S in theorem 5 has the form B is equal to S into A. Example 11. Consider the group set 12 under the operation addition modulo 12 with the generator A is equal to 1. Find the order of the cyclic subgroup generated by 3 belongs to set 12. Solution. We use theorem 5. Here A is equal to 1, n is equal to order of set 12, which is equal to 12. If H is a cyclic subgroup generated by 3, then B is equal to 3 and B is equal to 3 is equal to 3 into 1 is equal to S into A implies S is equal to 3. Hence, D is equal to GCD of n comma S, which is equal to GCD of 12 comma 3, which is equal to 3. And therefore, H is equal to subgroup generated by 3 has n by D, which is equal to 12 by 3, which is equal to 4 elements. We can verify the above by listing out all the elements in H is equal to subgroup generated by 3. They are 1 into 3 is equal to 3, 2 into 3 is equal to 6, 3 into 3 is equal to 9, 4 into 3 is equal to 0. So, subgroup generated by 3 is equal to set consisting of 0, 3, 6, 9. Corollary. If A is a generator of a finite cyclic group G of order n, then the other generators of G are the elements of the form A raised to R, where R is relatively prime to n. Proof. If B is equal to A raised to S is a generator for G, then the cyclic group generated by B is G and has n elements. By theorem 5, the cyclic group generated by B contains n by D elements, where D is equal to GCD of n and S. These two lines gives n is equal to n by D or D is equal to 1, that is GCD of n and S is equal to 1. Therefore, the other generators of G are the elements of the form A raised to R, where GCD of n and R is equal to 1. If the operation is additive, then A raised to R above has the form RA. Example 12. Find all generators of set 18. Solution. By theorem 4, we know that 1 is a generator of set 18. Now, by the corollary to theorem 5, the other generators are given by R into 1, where R is relatively prime to 18, and they are 1, 5, 7, 11, 13 and 17. Hence, subgroup generated by 1 is equal to subgroup generated by 5 is equal to subgroup generated by 7 is equal to subgroup generated by 11 is equal to subgroup generated by 13 is equal to subgroup generated by 17, which is equal to set 18. Remark. In view of corollary to theorem 5, if A is a generator of a finite cyclic group G of order n, then the number of generators is given by phi of n. Example 13. Find all subgroups of set 18 and draw the lattice diagram. Also find all the generators of each subgroup. Solution. Since set 18 is cyclic, all of its subgroups are cyclic. The numbers less than 18 and relatively prime to 18 are 1, 5, 7, 11, 13 and 17, and they are the generators of set 18. The cyclic subgroup generated by 0 is set 0, which is equal to subgroup generated by 0. In order to get other proper subgroups, we start with 2 and get subgroup generated by 2 is equal to set consisting of 0, 2, 4, 6, 8, 10, 12, 14, 16, which is of order 9. The other generators for subgroup generated by 2 are R into 2, where R is relatively prime to 9, and those values of R are 1, 2, 4, 5, 7 and 8. Hence, the generators of subgroup generated by 2 are 2, 4, 8, 10, 14 and 16. The element 6 of subgroup generated by 2 generates set 0, 6, 12, and 12 also is a generator of this subgroup. We have so far found all subgroup generated by 0, 1, 2, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14 and 16. This leaves just 3, 9 and 15 to consider. Now, subgroup generated by 3 is equal to set consisting of 0, 3, 6, 9, 12, 15 is a subgroup of order 6, and since 15 is equal to 5 into 3 and GCD of 6 and 5 is equal to 1, 15 also generates subgroup generated by 3. It remains to consider 9, and we can see that it generates subgroup generated by 9 is equal to set consisting of 0, 9. Let us summarize what I have discussed in this session. In this session, we have familiarized with the concepts of cyclic subgroup and cyclic groups. We have noted that all the elements in a cyclic group can be generated by a single element. Structure properties of finite and infinite cyclic group are also discussed. Now, try to answer the following questions. 1. Show that set P has no proper non-trivial subgroups if P is a prime number. 2. Show that a group with no proper non-trivial subgroup is cyclic. 3. Give an example of an infinite group in which each element is of finite order. 4. Write at least 5 elements of each of the following cyclic groups. A. 25 set under usual addition. B. Set consisting of 1 by 2 whole raised to n belongs to set under usual multiplication. C. The set consisting of pi raised to n such that n belongs to set under usual multiplication. Hope you enjoyed this section. See you next time. Till then, take care.